So in the last several lessons, we've been talking about electrolysis. Electrolysis is an electrochemical method in which you use electricity to drive a non-spontaneous redox reaction. So it's an electrochemical process because it involves interfacing electricity with redox chemistry. And in this case, it's non-spontaneous because you're providing electricity, which is actually the energy to drive the process. So as I've shown you, we can do quite a lot of things with electrolysis. We can generate pure metals, we can electroplate materials. What I'd like to talk about in this last lesson is how we think about electrolysis from a quantitative perspective. So as soon as we are providing an energy input, we have to think about the costs of our process. How many reagents do we have? How much energy are we providing? How much is the overall process costing us? If we're going to engineer a process to be effective to make a product, we have to be worried about all of those things. And that's what this lesson is really focused on. So you know already that electricity drives all electrolytic cells. So that means that in a sense, we can think of electrons as a reactant in the electrochemical processes that happen in electrolytic cells. So, we write electrons as a reagent in redox reactions. We can actually even quantify them, right, in terms of physical properties. So we can use the electrons and the stoichiometry of chemical reactions to talk about things like yields of reactions and efficiencies of reactions and amount of reagent consumed. And that's what I'm going to show you in this lessons. The only way this is different from the other types of stoichiometric problems that you've seen so far is so far you've only solved stoichiometric problems with chemical reagents. So you've been able to think quite simply in terms of mass of a chemical reagent or quantity or moles of a chemical reagent. Mass of electrons is not a useful concept. And so instead, when we are thinking about electrons, we think in terms of total charge of the collection of electrons, because the total charge can be connected back to quantity of electrons via the mole using Faraday's constant. So that's what I'm going to do for you in this lesson, is to look at a few of the different types of problems that we can solve using that relationship between charge of an electron, moles, and stoichiometry of a reaction. So let's start from a simple reaction. We talked in the last lesson about electroplating. This is the reaction that happens at the cathode in an electrolytic cell in which we're electroplating silver. Basically, we start from silver ions. They are reduced by a single electron to generate solid silver metal. And this is a good way to make a precious metal coating on the outside of a base metal. Silver is commonly used because it's the cheapest of the precious metals. So it looks nice, it's unreactive, but it's still relatively inexpensive. It's a lot cheaper to coat something with silver than it is with gold or palladium. What I'd like to do in the next few minutes is to look at this reaction from a stoichiometric perspective. And the question that I'm asking is, what quantity of silver is electroplated if a mole of electrons flow through the electrolysis cell? So this is really a very simple question that's just based on the stoichiometry of the reaction. The stoichiometry of this reaction, the coefficients in this chemical reaction, are just that 1 mole of silver ions reacts with 1 mole of electrons. So if a mole of electrons flow through the electrolytic cell, you can reduce precisely 1 mole of silver ions. Once you've understood that, all these problems become simple because they're really just stoichiometry problems, just like the other kinds that you've been solving earlier in the class. So let's look at a specific problem then. What quantity of electrons in moles is delivered by an electrolysis cell operating at a 5 amp current for 30 minutes? This question doesn't rely on the chemical reaction at all. This is really just a physics problem asking us to use Faraday's constant together with a current and a time to determine how many electrons have been transferred somewhere. So let's see where we start from. We start from 5 amps of current. Remember that an amp is a coulomb per second, right? An amp is always a unit charge per unit time. So 5.0 coulombs per second. And this is where we now need Faraday's constant. Faraday's constant is 96,485 coulombs per mole of electrons. So what we now have, if we were to complete this problem at this point, is the number of moles of electrons that have been transferred in a second at that current. But the problem's not interested in seconds, it's interested in 30 minutes. So we're going to need to multiply up to be thinking not just about 1 second of passage of current, but rather 30 minutes. So I solve these problems a lot. I happen to know that 600 seconds is 10 minutes, which means 1,800 seconds is 30 minutes. But you could do this more simply with 60 seconds is 1 minute. And now you need 30 minutes of your electrolytic process. So the seconds and the minutes, and you'll be left with an answer in terms of moles of electrons. So if we multiply 5 by 60 by 30, this is our 1,800 seconds multiplied by 5 divided by 96,500. Effectively, you basically get a tenth of a mole of electrons, so 0.093 moles of electrons. This is really just a stoichiometry problem in which we use the definition of current and our knowledge that a mole of electrons is associated with Faraday's constant. So the important thing that you notice in this particular problem is that a current multiplied by a time gives you charge. We then converted charge into quantity of electrons. That's an important relationship. You can use that again and again in solving electrochemical problems. Current times time, current times time gives you charge. From charge, you can go anywhere you like. In this case, we went from charge to moles of electrons. You could also use that to convert to mass, right? As long as you've got quantities, once you're into moles, you can use mole as a sort of shared currency to go in many, many different places. So now if we assume the cell in the previous problem is electroplating silver, what mass of silver will be electroplated? This problem is now super easy, right? Because we know there's a one-to-one stoichiometric relationship between moles of electrons and moles of silver. So we know that 0.093 moles of silver ions are electroplated. And we quite simply need to multiply that now by the molar mass, 107.87 grams of silver per mole of silver. So we expect our answer to be about a tenth of that. It turns out, in terms of significant figures, we can electroplate precisely 10 grams of silver in this process. And I gotta be honest, I didn't start from wanting to get 10 as my answer. I literally just picked these numbers randomly and it worked out to exactly 10. So this is probably one of my best written problems ever. But what you see is you can use the stoichiometry that you find in a chemical reaction, as well as this relationship between current passed and charge to determine the mass of a chemical reagent. And this is really just a simple unit conversion. So this is no different than any other stoichiometry problem that you've solved. It's just that one of the reagents is an electron. This is powerful because you can now predict things like how long will I have to drive the process in order to electroplate 100 grams? Or if I need to cover an object of a certain volume with a layer of a certain thickness, you could then calculate what mass of metal that would be, and you could figure out how much current you would need. So this is really a key tool in designing electroplating or other electrolysis types of applications.